Welcome back to our discussion on multiple alleles. And in this session, we are going to discuss about the inheritance of the blood group alleles. So, inheritance of the ABO blood group system is governed by three alleles, being multiple alleles. And these three alleles are designated as capital A, capital B, and capital O. And this was done by F. Bumstein. The autosomal gene that controls the blood group was designated as capital I, and the multiple alleles are designated as IA, IB, and IO. So these alleles are responsible for producing, or as we discussed in the previous session, the particular gene or its allele is responsible for producing the enzymes that will be adding the monosaccharides or the terminal monosaccharide, either N-acetyl glucosamine or galactose to the H substance. So here the IA allele produces the enzyme which will be adding N-acetyl galactosamine to the H substance, and IB will produce the enzyme that will be adding galactose to the H substance at the terminal end. And IO will produce no enzymes, and hence such individual will have or such individuals will be having only the H substance with the terminal fucose. They will be having a terminal fucose in them as with the H substance, or they have the H substance for the IO individuals. And coming to the dominant or the dominant and recessive relationship among the alleles. So, of the three alleles, IA and IB are found to be co-dominant over the recessive allele, which is IO. And IO is the wild type allele, and the other two are generated as a result of or originated as a result of mutation from the wild type IO allele. So even though there are multiple alleles to control blood group, they follow the Mendelian pattern of inheritance. Mendelian pattern in the sense that, as you see here, that is the homozygous dominant as well as the heterozygous will be showing the dominant phenotype, and only the homozygous recessive will be showing the recessive phenotype. So this is the table which is given here, is depicting the pattern of Mendelian inheritance in this. So, if a person is having type A blood group, as we said, IA is a dominant allele. As a result, the homozygous as well as the heterozygous, that is IAIO, will be having the blood group which is type A. Coming to the B blood group, the same is applicable to B because B is also dominant A and B are co-dominant to O. As a result, IB, which is a homozygous condition as well as the heterozygous condition will be showing the same blood group which is B. AB being co-dominant, IA and IB, it will be showing the particular blood group which is called as AB. Being recessive, only homozygous condition will have or will show the blood group which is called as O. So this is the inheritance pattern. So the inheritance pattern is same as that of the Mendelian pattern of inheritance, which we discussed in the very first session. So this is about how they are being inherited, and regarding the inheritance of the blood group alleles, we will be discussing few examples on how this blood group alleles are inherited to the next generation by different blood groups. So we will consider a few examples. So in the first example, so this is these are two examples in this particular box. So this is, we are going to cross AB and AO. AO means it is a heterozygous for A blood group, and this is AB. So in this, there will be two gametes, IA and IB. In this case also you have two gametes, IA and IO. So you plot a Punnett square for with two gametes each, and you have uh, four different mainly three different blood groups are likely to occur. So IAA and AO, they fall under the A blood group. You have the AB blood group and the BO, which is the heterozygous for B blood group. So these are the three possibilities. And the second case is the crossing of the heterozygous for A as well as the heterozygous for B. In this case, you can see that all the four blood types are possible in such cases. From the Punnett square, you can see AB, the heterozygous for B, heterozygous for A and O. So, this is another example. So here, a man is having heterozygous for A and the woman is AB. And you can see the gametes which are here you have two types of gametes, A and O, IA and IO. Here also you will have two alleles, IA and IB. So here in all these examples they have just put the alphabets as the alleles, but when you are doing the problems, please take care that you write the alleles perfectly as IA, IO, etc. So here the gametes and crossing will result in the offsprings. These are A blood groups, this is B blood group and AB blood group. So these are the three possibilities, three probable blood groups when this couple or when there is a child for this particular couple, the possible blood groups are. So this is how you derive the inheritance pattern of derive the inheritance pattern of the ABO blood group system. So these were the few examples regarding. So this is the same. The crossing and the Punnett square, etc. They are same as that of the normal Mendelian inheritance. They clearly follow the normal dominance pattern or the dominance relationship, as in the case of the Mendelian inheritance. So in the so next is our discussion. So this is with the inheritance pattern of the blood group, and next is we are going to discuss the another type or another antigen which is taken as an important factor during blood transfusion, that is the RH blood group. So RH is also based on an antigen. As we discussed in the previous session, the ABO blood group, it is based on two antigens which are present or absent in the blood or the RBC, the membrane glycoprotein or glycolipid of the RBC. So here this is based on another type of antigen which is called as the RH antigen. So the RH blood group is named because the RH antigen was first discovered in rhesus monkey. That's why it is called as an RH blood group and RH antigen. And it is believed that the alleles of three genes may code for the RH antigen. There are three genes, and the alleles of these three genes, they code for this particular RH antigen. And it is also known that these three genes lie very close in the chromosome, in the homologous chromosome. Their locuses are very close, and hence they move together during crossing over. Move together in the sense that there is less possibility of crossover between uh, these three genes. As a result, they behave as a single gene during crossing over. Behave as a single gene does not mean that they can be considered as a single gene. They are three different genes, but because of their very close position, if they are getting if they are being, or that particular area or particular locuses are being involving in crossing over, all the three genes together will be transferred, or together will be recombined in the or it will involve in a recombination. So that's why the genes, that is the importance, because the genes lie very close together in the chromosome, and they are moving together during crossing over. So people whose RBC is having RH antigen is designated as RH positive, and those individuals who do not have the RH antigen is designated as RH negative. So normally the blood plasma do not contain the anti-RH antibodies, as we saw in the case of ABO blood group system, where the microbial antigens trigger the formation of the antibodies against the RBCs because of cross reactivity or similar antigens present on both. Such a case is not seen in the case of RH antibody. That means the blood plasma naturally do not contain any antibodies for RH antigens. So if an RH negative person receives an RH positive blood by transfusion, The reverse is not possible. As I said, the reverse might not happen. That is, if the person is Rh positive and is taking Rh negative, because there is no antigen in Rh negative, that might not create much problem. So, if an Rh negative person is receiving an Rh positive blood by transfusion, the immune system of the negative person will start making anti-Rh antibodies that will remain in the blood. And in a second transfusion of Rh blood is given later, the previously formed Rh antibodies will cause agglutination and hemolysis of the RBCs in the donated blood, and a severe reaction or a hemolysis may occur. Hemolysis and the other complication, as we discussed earlier, may occur. So this Rh compatibility is also important or taken as an important criteria during blood transfusion. And the common Rh antigen is usually designated as RHD, and its antibody is designated as anti-RHD. The Rh antigen production is controlled by the dominant gene capital R. When the gene is recessive, it does not produce the antigen. That means that is Rh negative. And they are also, this is also inherited in the normal Mendelian pattern, where the homozygous and the heterozygous individual, as you see here, capital R and capital R small r, they will have the Rh antigens and they are Rh positive, and the homozygous recessive, they are Rh negative. So the importance of Rh blood grouping or Rh compatibility is discussed in this particular context, which is the hemolytic disease of the newborn (HDN) or erythroblastosis faetalis. So this is a most common problem with Rh incompatibility, and that is called as a hemolytic disease of the newborn, and that may arise during pregnancy. This usually occurs when a mother who is Rh negative carries an Rh positive blood. That means when a woman marries an Rh, or an Rh negative woman marries an uh, Rh positive man, there are chances that the child can be Rh positive. There might be two conditions like this might happen if you take the condition. So woman as Rh negative means the woman will be always will be small r, okay, that is Rh negative. And if she is marrying an Rh positive individual, Rh positive means it can be either homozygous, okay, or it can be, or he can be heterozygous. Okay, so if the person, or if the husband of this particular girl is, or this particular woman is homozygous as capital R, if this is the particular case, that is, if the woman is Rh negative and the husband is Rh positive with the which is homozygous, always the fetus which is formed will be surely Rh positive, because always heterozygous individuals or heterozygous fetuses will be the result in such a marriage. And in this particular case, if he is heterozygous, there is a chance that the fetus can also be Rh negative. So we'll first discuss the case where the particular person, we'll take the husband of that particular woman to be Rh positive, which is homozygous. So if that particular individual is homozygous for Rh antigen, what happens is that all the conceived fetuses will be Rh positive, and the woman is Rh negative. So what happens is that in the first pregnancy, that will not result in any complications, because the fetus and the maternal blood does not mix, because there is a well formed placenta, and the placenta restrict the mixing of blood. Only the exchange of the important materials which are required for the growth and nourishment of the embryo will be passing through the placenta, with some antibodies etc. also will pass uh, through the placenta. Other than that, there is no mixing, direct mixing of blood to the placenta. So the first pregnancy, as you see here, this will not the first pregnancy, as you see in this particular diagram, this will not create a problem. The first Rh positive fetus and Rh antigens are present in the fetus, and the woman is Rh negative, and there is no leaking of Rh or mixing of Rh positive blood and Rh negative blood till the last stages of pregnancy. But what happens is at however, a small amount of Rh positive blood leaks from the fetus through the placenta into the bloodstream of Rh negative mother, and the mother will start to make antibodies. This happens at the during delivery or parturition. That means when the placenta is being separated from the mother, when the during delivery, what happens is a small amount of blood mixes. Until then the child will not have any problem. The child will not be affected because there is no mixing of blood. But at the time of parturition, some amount of blood will be mixed, and during at the time of parturition, the mixing does not affect the first child because already the child is at the stage of delivery, and that mixing of blood is not going to cause any harm to the first baby. So in such cases, the first fetus and the first baby will not suffer with any complications. There will be no much complication for the first baby, and you can see that after the baby is delivered, the Rh positive blood is mixed with the Rh negative blood of the mother. As a result, the mother's body, after the delivery, the mother's body, this is between the pregnancies, the mother's body will be producing anti-Rh antibodies that will be present in the plasma of the mother. So that will not also cause any uh, reaction in the maternal body, because the antibodies are generated against this Rh positive, some amount of Rh positive blood. The mother being Rh negative, she will not suffer from any complication having this Rh antibodies in her. And the all the problems arises in the second pregnancy if the Rh incompatibility is not or Rh incompatibility is not being monitored. So what happens in the second pregnancy is that when the second fetus is conceived, and the second fetus, surely in this case, if you are considering this particular case, surely this particular fetus also will be Rh positive, and such a fetus will have the antigens when blood is being formed and when the circulatory system starts to function. The blood will have its Rh and antigen on the RBC, and what happens is the antibodies, they can cross the placenta, even though the blood does not cross. As I said earlier, the nutrients and all the essential requirements of the for the fetus will be passing through the placenta, and also some antibodies can also cross through the placenta, and that antibodies will reach the second fetus, and that will result in hemolysis. All the RBCs of the second fetus will be destroyed, and that will result in hemolysis, and that hemolysis will cause the death of the or the premature death of the baby in utero, and that is why it is called as hemolytic disease of the newborn, because it is also called as blue baby disease, because hemolysis has occurred. As a result, there is no RBC, normal RBC left, and hence the baby might appear blue in color. And this is also called as erythroblastosis faetalis, because the all the erythrocytes is being destroyed by the antibodies. So this is strictly monitored in nowadays. So if you take the second case, that is, if the husband is heterozygous for Rh antigen, you can expect two cases. That means the baby can either be Rh positive or it can be Rh negative. If the baby or the fetus is Rh negative, because if the husband is heterozygous, The fetus can also be Rh negative. If the fetus is Rh negative, the second fetus, if it is the Rh negative, it will not cause, because the antibodies will not be attacking, because there is no antigen for an Rh negative individual. As a result, if the second baby is Rh negative, it will not, the antibodies which are formed will not cause any problem. But if it is a homozygous condition or the heterozygous condition itself, if the second fetus also happens to be Rh positive and this is not monitored, the Rh blood grouping is not monitored, this will surely result in this particular condition, which is called as the hemolytic disease of the newborn or erythroblastosis faetalis. So, so what is done for this, or how can you prevent this? So nowadays, our blood groups and the RH factors are strictly monitored. As a result, if the woman is Rh negative and her husband is Rh positive, what is done is that an injection of an antibody, which is called as an anti-Rh antibody, is called as anti-Rh gamma globulin, and that is the trademark of the company, which is given ROGAM, can be given to prevent this hemolytic disease of the newborn. And how this act is that all the Rh negative women will receive this Rogam injection soon after the delivery, or if it is unmonitored after the miscarriage or abortion. Now, soon after the delivery, also it is usually given so that the second baby or the second fetus is not affected. So these how these antibodies work is that it should be given soon after, either soon after the delivery or soon after miscarriage or abortion in this particular case. So these antibodies bind and inactivate the fetal antigens, because it is a fetal antigens that is going to trigger the mother's immune system. So this triggering is blocked by these antibodies. They will be inactivating the fetal antigens before the mother's immune system will respond to it, to the foreign antigens, by producing her own anti-Rh antibodies. So, so this is how the hemolytic disease or the erythroblastosis fetalis can be prevented. So, with this, we come to the end of the discussion of the Rh blood group. So, in the next session, we'll be discussing about a rare type of blood group, which is called as Bombay phenotype.